Hi, my name is Jack Beckwith, a recent MSci Geoscience graduate from Royal Holloway. I'm here to present to you the work of my major fourth year project, What Processes Drive Voluminous Granite Generation? Insights from Scottish Cumulates. I must thank my project supervisor, Christina Manning, and also Matthew Thirlwall, for without their help and insights this project would not be possible. To begin, I'll be contextualising this research by discussing the geological background of the study. I'll then introduce the aims of the project, the methods used, and the motivation for conducting it. And following this, I'll tie the results of the project with discussion before concluding with a simple summary model. Appinite suites or complexes are recognised globally, with the term generally applying to minor mafic intrusions and placed proximal to coeval felsic plutons at continental settings. Prior work has noted mineralogical and textural features of the mafic components that are indicative of hydrous magmas. Calc-alkaline to socionetic geochemical affinities typify these suites, features that they share with TTG rocks of Archean continent terrains. On the basis of this, a general two-stage model has been proposed for their formation, involving extensive metasomatism of the mantle wedge, followed by the development of a slab window inducing melting of the lithospheric mantle. Specifically, this study focuses on accumulates found at the Appinite suite of Western Scotland, Kentallenites and Appinites. Considering the temporal, spatial, and geochemical similarities between the mafic and felsic components of this suite, it has been proposed that there is a close genetic relationship between the rocks. Furthermore, geochemical similarities with Archean TTG rocks suggest that these cumulates could provide an insight into the evolution of the crustal magmas, and potentially analogous to Archean continent formation. The aims of this project are to explore the genetic relationship between the cumulates, and ultimately to better define the crustal storage and evolution of these rocks. These lesser explored rocks provide valuable information regarding the crustal processes involved in hydrous granite generation, with mineral analyses revealing information otherwise hidden by whole rock analysis. This not only has implications on modern systems, but Archean systems, where 60 to 70% of our continental mass was produced. The two methods employed here were textural analysis and geochemical analysis. Textural analysis involves descriptions of the mineralogy and textures of thin sections under a microscope, and a thin section of each of the two rocks were then digitised and statistically analysed, but is omitted from this presentation for the sake of time. A mass spectrometer was then used to target minerals of interest, which is a laser that ablates the thin section to collect their chemical signatures. Multiple drills of mineral standards were conducted throughout each run of the laser, allowing us to calculate errors from both short and long-term instrumental disturbances, ranging from various laser effects to machine drift. Jumping straight into the textural analysis, the Kentallenite show olivines, clinopyroxenes, biotites and feldspars, however omits amphibole that is typical of the Bowen's reaction series. This is something we'll explore soon in a geochemical part of this talk. We see euhedral oscillatory zoned clinopyroxene megacrysts, indicating a prolonged crystallization period in the melt, with zoning corresponding to compositional changes, and so as identified for lasering. The Appinite is a much different scenario. We notice the lack of olivine, moving towards a more felsic composition, but the presence of hornblende, otherwise missing in the Kentallenites. The textures are particularly important in this rock, with a whole host of disequilibrium textures. Clinopyroxene is often sieve textured, indicative of magma mixing, that also show similar oscillatory zoned grains as in the Kentallenite. Other grains have undergone fluid alteration and replacement, and notably the presence of granophyre is evidence that granitic compositions can be made from these melts. Only the clinopyroxene geochemical data will be discussed here, as they provide the most insight into the evolution of the melts from which they crystallised. The above graph provides simple comparisons to be drawn between rim and core compositions, as well as between the two cumulates. The x-axis represents individual grains analysed from core to rim, with their respective Mg numbers shown on a y-axis. And this Mg number is valuable because a shift to a lower value generally corresponds with crystallisation towards a more evolved felsic melt. On the left partition of the graph, we can see the Kentallenite clinopyroxene core compositions vary that all have rim compositions around 80, implying mixing of high and low Mg number cores towards a common melt composition. The decreasing trend of Mg number from core to rim in the Appinite is more consistent with fractional crystallisation. The trace element spider diagrams above show relatively parallel lines, indicating a common melt source, with slight crossovers visible on the profiles, indicating grain relationships as anticrysts rather than xenocrysts, and so any mixing is likely to be of genetically similar magma. The right graph shows a relatively linear trend between titanium and vanadium. Their properties mean that they are uninfluenced by fractionation, and so a similar ratio between the cores are indicative of a common melt source. Considerable negative niobium anomalies are typical of arc magmas, and variation in fluid mobile elements is consistent with the tectonic model mentioned earlier, influenced by flux of sediments and volatiles. The Appinite data shows trends typical of fractional crystallization. The above graph plots Mg number against various elements to assess this, and we see increases in relatively incompatible elements, sodium and manganese, and decreases in compatible elements such as nickel and strontium from core to rim, as crystallizing mafic phases preferentially sequester the latter elements from the melt. Similarly, a negative europium anomaly is obvious for the rim compositions, as plagioclase later incorporates europium. You'll notice that the rim compositions for the Kentallenite do not follow such trends, with sodium concentration much higher than expected and manganese values being closely distributed. One process that could explain these unusual rim compositions could be subsolidus diffusion, essentially where an adjacent grain's chemical signature bleeds into another. The above graphs represent transects of multiple drill sites from core to rim on zoned pyroxenes and Kentallenite, and that's shown on the bottom left image. You'll notice that neither fast or slowly diffusing elements conform to such a tight range of values like the Mg number does at the y-intercept, ruling out diffusion as playing a key role here. Rather, the changes in Kentallenite rim values are likely attributed to the role of a mineral buffer, where a mineral with a sensitive range of stability controls the chemistry of the melt. Recent work has suggested the presence of an amphibole sponge in arc environments, a so-called cryptic fractionating phase that we do not see in the rocks. And this can make sense here since we do not have any amphibole in our Kentallenite, but we do in the Appinite. Here the buffer controls melt chemistry by partitioning aluminium into hornblende and limiting the aluminium and magnesium ion ratio of the melt, whilst enriching it in sodium. The diagram on the right simplifies the path of magma ascent through the amphibole field, whereby the Kentallenite amphiboles are resorbed as it exits the stability field. This interpretation is in contention with the magma mixing of two unrelated magmas to hybridize the rim compositions, and better explains why certain elements are constrained whilst others are not. Evaluation of the textural and geochemical differences between cumulates has shown that results are consistent with fractional crystallization being the dominant differentiation process, with minor mixing. Their journey begins with secondary melts of arc-related magmas. Olivine and clinopyroxene nuclei early, with hornblende crystallizing as the melt rises. The Kentallenites experience lesser degrees of fractional crystallization, rising slowly and causing hornblende to be resorbed as a cryptic phase. Conversely, prolonged fractional crystallization shifted the Appinites to a more felsic, volatile-rich composition, whereby hornblende was quenched. It's expected that a continuation of this crustal process can feasibly explain the generation of nearby balahulish granites. And considering the prevalence of hydrous assemblages and a geochemical similarity shared with Archean TTGs, it is expected that fractional crystallization at arc settings may have been responsible for the formation of Earth's earliest continents. Thank you for listening to my talk. If you have any questions, please feel free to contact me.